Greetings! I've been talking about this 10 GHz tower-mounted transverter system in the last several videos. It's about time that I show you some block diagrams of the system for those of you who are kind of lost on what I'm building. We can start with a high-level block diagram of the transverter system. Let's look at the transmit path first. For intermediate frequency radio, so the baseband radio, I'm going to be using an IC705 at 144 MHz. So I will be sending 144 MHz, about 500 milliwatts, into an attenuator in transmit mode so that I get only in the milliwatts range into a balanced mixer that's up on the tower, including the attenuator. Attenuator also is up on the tower because it's a switchable attenuator. And also sent into the balance mixer a local oscillator that produces 10.224 gigahertz. It's a constant carrier, it's a local oscillator, so the mixing of the 10.224 and the 144 megahertz IF signal, whether it's CW or sideband or whatever, will yield a 10.368 gigahertz transmit signal. And I'll have to boost that signal, which is in the milliwatts range, up to 10 plus watts, and that will be sent into, which you saw in one of my previous videos. So this is the transmit path, and obviously the receive path is very similar, except that we receive a signal at 10.368. It has to be boosted up with a low noise amplifier, or receive preamp if you like, before being sent into our balance mixer. The balance mixer will, with the addition of our local oscillator still at 10.224 gigahertz, produce a 144 megahertz IF signal. It's a receive signal, so it's quite low, and that's sent down the tower to the shack into the IF radio, the IC705. So that's really a high level. Now, when we look at the detailed block diagram, that's where the fun begins. If you have seen a similar video in my previous series from 2024 on my portable 10 GHz system, you will see much of what's here being the same as what was shown in that last year video. There are a couple of changes though. So what's identical? The transverter itself. It's the W1GHZ transverter, exactly the same unit. I use the same LO chain also, so a 10 MHz OCXO, a 3408 MHz synthesizer based on an ADF 4351 IC. I also use the W1GHZ tripler board, which will produce our 10.224 GHz LO signal. So what's slightly different now? For one, as I mentioned, I'm now using an IC705, which brings in an additional challenge, which we're going to see in a future video. So the IF radio is a transceiver, so the RF goes both ways. I need to have a switchable attenuator, same that I had before. This time the gain will be 33 dB, and it will be designed on a custom-made PCB as opposed to a universal board that I use in my portable system. So you'll see this in a future video as well. So the IF radio will send around 500 milliwatts. I'd like to have 500 milliwatts up on the tower, so I'll probably have to boost the transmit power a little higher, of course, because of coax losses. So in order to hit the right sweet spot for the amplifier and get out our full power, 33 dB of attenuation is the desired attenuation. And of course, when we are in receive, that attenuation has to be removed. So it's a transfer relay that will simply let the receive signal through, but attenuate when we're in transmit. And that's switchable using a sequencer, of course. So with the proper signal here at -16 into the transverter, we split, and in transmit, +5 dBm is what we get, assuming -16 here. Now +5 is too hot For the next stages, I need to attenuate by 10 decibel. So I get -5 here. That's at 10.368, 10 gigahertz, right? Attenuate 10 dB. It's an inline attenuator, coaxial attenuator, into a gain block, a little amplifier that's required because the transverter cannot push hard enough. I need plus 15 dBm into the power amplifier, and this guy can produce a maximum of around plus 10. So I needed to attenuate and then gain boost by around 20 dB. That's what the little amplifier does, which brings in plus 15. And finally, after the big power amplifier, which has a 25, 26 dB of gain, I get plus 41 dBm or around 12 watts. If I get 10, I'll be happy. But I could actually push to 14 in a non-linear way, like CW, but 12 is still linear enough, into a coaxial relay and out, of course, to the antenna. Now, in the receive path, it's the similar as before. I go through the relay, in receive, controlled by the sequencer, of course, into a low noise amplifier, and into the transverter, and then down to 144 megahertz out to the radio. So those are the changes that I had to make. Adjusting transmit power, different power amplifier, which you've seen already, and the addition of an MMIC gain block, a small amplifier made in China. It works okay, and it only draws 50 milliamps. So it looks like a good little beast. Time will tell, of course, but for now it does the work. So that's for the RF side of the business. Now for the control side, I will give you a little teaser, but in the next video I will detail this block diagram. Essentially, we will have 2 Raspberry Pi Picos, so 2 controllers, plus a PC software running in the shack. So 1 Raspberry Pi Pico in the shack, and 1 Raspberry Pi Pico up on the tower to control the various items that are there. In addition to the 2 Raspberry Pi Picos, I'll have a software running on the PC to control these 2 units, allow for transmission or stop the whole system, and so on. That PC will also have a USB link to the ICOM 705 IF radio. It will allow me to send Morse from the PC just by typing strings directly to the ICOM 705 as opposed to manual keying with a paddle. I'll also have a paddle, of course, if I want to send something manually. Another USB link will be used to control the local Raspberry Pi Pico through a USB to UART converter. The Raspberry Pi Pico will take care of detecting the PTT coming from the radio through an interface circuit and allowing the ICOM 705 to transmit RF power only and only when the whole system is ready in transmit mode, ready to put out a lot of power. So that's an important function here from the local Raspberry Pi Pico. The remote Raspberry Pi Pico, of course, will sequence the various devices, low noise amplifier, coaxial relay, 8 volt for transmit, 8 volt for receive, power amplifier, and even a cooling fan if necessary. So that Raspberry Pi Pico will be pretty busy, and there will be coordination between the 2 by sending messages through an RS485, so it's one twisted pair, RS485 link between the 2 Raspberry Pi Picos. So that's how this guy will know when it's time to let the ICOM 705 transmit, for example. It will receive a message from the remote saying, okay, go ahead, I'm ready. And then when this guy goes into receive, it will tell the remote guy, okay, going into receive, and this guy will transition the various signals to go into receive. So in addition to sequencing, so controlling the various RF elements, it will also control the steering actuator for the dish orientation. I'll show you that in a future video, but it's essentially a short actuator that will allow me to tweak the dish orientation because the main rotator on the tower itself, tail twister, doesn't have the accuracy to get into that kind of accuracy pointing plus minus 2 degrees worst case. So the remote Pi Pico will also control the actuator when it receives commands from the PC software through the local pipe eco, it will orient the actuator. And I'll also have some temperature sensors, because this enclosure in which the whole system will be contained up on the tower will heat up quite a lot. It will be at least 80 watts of power dissipation in transmit. So it's a lot of heat. I'm still wondering how I'm going to do it. It's not obvious. All right, so that's the high-level control. In the next video, I'll dig more into a lower level of the control, and I'll show you the controller board that I designed. All for now, 7-3.